What's up, everybody? Welcome to part 5 of this tutorial series on using the KITTI Odometry dataset with OpenCV and Python. So we have so far got our data together. We have been able to get depth estimations from our stereo pair of cameras, and now we have just learned how to match visual features in subsequent frames, and now we can use those matches in order to figure out the change in camera pose between the two frames and then sequentially draw a trajectory of the car over time from frame to frame. And we're going to do that by using the SolvePnPRansac function from OpenCV, and I'll explain how that works in just a second. So I won't spend too much time talking. We'll just kind of dive right in today. I think this video might be a little shorter because maybe I'll just cover this, how to do this on one frame, and then in the next video maybe we'll do the iteration over the entire data set, or we'll just see how far I can get. So here we are back where we left off last time, where we were matching features between this and the subsequent frame, and we can see that the SIFT detector was working a lot better than Orb. Orb was not giving us high quality features, and I'm not quite sure why, but so we're going to be using SIFT. And I won't backtrack too much. If you've been following along, this is where we left off. And so the idea here is that in the very beginning, in the first video, I was explaining how when you're projecting the 3D world onto an image plane, you're essentially dividing the depth information out of the 3D world, which shrinks everything toward the camera onto a flat plane, which everything has a depth of 1. And so now you've lost all your depth information, but you've managed to position everything on a flat image that represents what the 3D world looks like to the camera, or to the observer. And so the reason we went through all the trouble of getting our pixel-wise depth estimations from our stereo pair of cameras is that when we do these feature matches, we want to re-project these 2D image coordinates back into a 3D world so that we have some estimate of the X, Y, and Z location in the real world of the image features in the first frame, because essentially what we'll be doing is we're using the camera's position in the first frame here as the global coordinate system, and then we're going to use the SolvePnPRansac function to solve for the change in pose of the camera, which allows the features that we're tracking in the global coordinate frame to appear in their new locations on the 2D image of the camera's second position, so the frame after this one. And the way that we do that is just by multiplying the depth back in to the 2D points in this image. So using this SIFT feature detector, it's going to give us a list of matches where it gives us the pixel coordinates of the feature that we're tracking and matching into the next frame. And so since we have pixel-wise depth estimation from our stereo pair, then any pixel location of a feature that we're tracking, we have a depth for, ideally. I mean, we have some errors, so we'll just filter those right out and ignore any feature locations or key points that are associated with inaccurate depth. We're going to ignore those. And we compared before to make sure that our stereo depth estimations were lining up with what the LiDAR told us, and indeed they were matching up quite nicely, so we know we did things right. And so all this will do is we'll take these pixel locations, we'll do a little arithmetic to multiply the depth back into those 2D coordinates to reproject them into 3D space, and then we'll use an algorithm to solve for the pose of the camera here that would make the most sense to explain where those same features are now found in the new image plane of the camera's new coordinate frame. So we'll go ahead and get started here. Let me minimize that. Okay. So essentially, we're going to have a function that estimates the motion of one frame, one subsequent frame, and we'll call that estimate motion. And then we're going to need our matches. We're going to need the list of key points for the first image, list of key points for the second image, and K, which is the intrinsic matrix of the camera, which I went into in the first video. And then we'll want the depth map for the first picture. So the first frame that we're talking about, this is going to be done on every single frame. And in this sequence, there's like 4,541 frames or something like that. So it's going to be happening over and over and over again. And then we want to set a max depth equal to 3,000. I explained this before, but I'll cover it again real quick. Is because when we did this stereo depth estimation, essentially we're giving it a cutoff of 3,000 meters from the camera, which is pretty far. I mean, that's 3 kilometers. So, I mean, can you even see 3 kilometers, or would any visual feature that you might be tracking at 3 kilometers away really be a good feature to be tracking to do this? Probably not. So, when we looked at this histogram over here, the numbers are actually being hidden right now. So, yeah, let me just fix this real quick, because let's say I could have done this a different way, but just want you to be able to see the numbers here. Okay. So we can see that all of this part of the histogram over here is all a result of when it didn't have a good disparity. So if we look at our disparity map here, like for instance here in this purple rectangle, it doesn't have disparity because the right camera doesn't overlap with the image of the left camera here in this rectangle. So this is like the baseline difference between the two images. And then we can see that what it gave us is this -1 value, which is basically an error. And so later on, we set anything that was -1 to be 0.1, which and anything that was 0 as well, which is no disparity, which is useless. And this 0.1 ended up giving us these maximum depth values of 3861 meters. And so we know basically that anything past 3,000 meters is just trash. We don't want it because it is not containing good information. So we're just drawing a dotted line here and ignoring any locations that had a depth of over 3,000 because it won't be helpful to us and it'll throw our calculations off. So that's the parameter that I'm setting down here with max depth equals 3,000. And you'll see that in just a second. So essentially what we're going to be wanting to return is a rotation matrix, which is a 3x3 matrix like we've been talking about. And so I'll just kind of throw a little dummy up here so we have an idea of what we're looking for. And then we want the translation vector, which is going to be a vector of size, or an array here, but 3x1, because eventually we're going to horizontally stack the 3x3 rotation matrix with the 3x1 translation vector, because that is altogether a transformation matrix. It's a 3x4 transformation matrix, which is exactly the format of pose that the data set uses for its ground truth, which we went all into in the first video, so you've heard. Yeah, so essentially we have our matches coming into the function here, which will be what we're returning from match features function that we made before. And so we want to get the points out of the matches because these matches are objects. So we'll make a item here, image1 points, and we'll make float32 array of. So we'll go into our list of original key points because we're getting our key points from the extract features, and then this extract features function is returning key points and descriptors for the image that we pass into it, and then we're matching our features based on the descriptors by using brute force matching, which is essentially just finding the distance between the descriptor vectors of the key points. And so these matches are associated with these key points that we had before. And so we need to basically index into our key point lists using the indices from our matches. So we'll say m.query index because query image is the first image. And then we'll say .point because that's the class variable name that we're going to be looking for off of that. Because if we look at, let me pull up a list of key points here. So if we say, KP1, what does this look like? Okay, so it's a list of these key point objects. What are attached to those objects? We have, no, that's not exactly what I was expecting to see. That's interesting. Oh, yeah, because we have to index in and get the first one, and then what is attached. Okay. Yeah, we can see we have, all of these variables that are attached to this particular class object. And so we're going to be taking the point, which is going to be a 2D coordinate in the pixel coordinates of where that point is. And so we're using the matches, so the index of which point in the first image that we are taking out of our list of key points for that image, so that this way we're keeping, really all we're looking for here is we're just trying to get a list of 2D coordinates of the features that we've matched. And so by taking the query index, we're finding the index of the matched point, for each match point that we're going through, and then we're going and extracting the key point location in pixels of where that match is in the first image so that we can compile this list of 2D pixel coordinates. So we'll say for m in matches. So I hope that's concise. And then we'll do the same for image 2 points. Again, this was supposed to be a float32. Float32. And then we'll say key points 2. Same thing, m dot, well, and this time we're going to do train index because that's the second frame in OpenCV, and then for m in matches. So essentially, yeah, here we're using our match to figure out where the index is in the second image, and then indexing our key points to make sure that we get the corresponding 2D pixel location of this particular match. Right. And so now we need to reproject these 2D points back into 3D space. And so we have our K, which is our camera's intrinsic matrix, and we'll just quick review. Should have auto-completed. Oh, it's just called handler. No attribute K. What have I done? Oh, it's stored as a projection matrix. Let me, I know I've got this here somewhere. Or maybe not. Well, anyways, we covered this in detail before. The K is the intrinsic matrix, and you know, I'll just go ahead and whoops. Hold on a second. I have a little organizational challenge here. Let's just go ahead and pull up this notebook over here so that you can see what I'm talking about. Keep this thing sort of inclusive here. I guess that's going to take a minute to load. Okay, here we go. This is the main notebook from the repository. Highly recommend that you read through all of it because it's all written out in explicit detail here. But okay, so here's the K matrix. It's the focal length in pixels in X, focal length in pixels in Y, and then the center of the image in X and the center of the image in Y in pixels. And these are used because, as we said before, when you're thinking about an XY coordinate of a camera, the origin's in the center, with Y going positive downward, negative upward, and X is going positive right, negative left. And so when we use pixel coordinates, 0, the origin is actually at the top left part of the image. And so if 0 was in the center of the image, or roundabout, then we need to basically add the center in the X direction and the center in the Y direction, because if this point in the top left is going to be negative Y, negative X, to then we're adding the center value of what the center pixel ought to be to this point over here to make both of those 0, right? So, and here's the thing is, you know, we have our depth, and so now we're able to take these 2D pixel coordinates and make them back into 3D coordinates, and we could do this by doing an inverse of the K matrix and multiplying that into, and maybe I'll do it both ways to show you, but the trick there is that doing the arithmetic by hand is actually a little faster, because when it comes to using NumPy to invert a matrix, there's a computational slowdown there, because it takes a minute for a matrix to be inverted by NumPy, and it's almost, well, in this case, it is easier on the computer to do the arithmetic just explicitly. And so what we can do is just pull the values that we need, which I just showed you over here. All of our relevant values that we need, we'll just pull them right out of the K matrix. So we'll say CX is K first row, first row, third column, right? And then CY equals K second row, third column. And then the focal length in X was K0, first row, first column, and the focal length in the Y direction, and these are in pixels, important to remember in just a second, and this is first, or rather second row, second column. And we can verify this right over here. There's FX, there's FY, CX, CY. So we're just pulling them out, assigning them to these variable names, so that we can use them in some hand-drawn arithmetic. So we're going to make a empty array for our object points, and these are going to be the 3D locations of the features that we're tracking. And so we're going to call it numpy.zeros, and we're going to say it's got 0 rows and 3 columns. And so there's essentially nothing there, but it already has a shape. And the reason I'm doing that is because we're going to keep stacking our new points on to this array, because we don't necessarily know how many rows we're going to have. Because for every frame that we do, we're going to have a big list of matched features. And we're going to find that some of those features are in locations for which we do not have good depth estimations for, and we won't be using those features. So when we come across that situation, we're going to just skip to the next feature. And so this will allow us to just keep appending the features that we are using onto this array, sort of like you would a Python list, except that we're keeping it in the array, data type. And we'll be doing this by keeping track of an empty list called delete, which will have the indices of the points that we won't be using. So we'll be going through each of our matched features, and we'll iterate through the image points in the first image, because it seems to make sense. So for I, U, V, which are pixel coordinates, as we went into in the first video, in enumerate image 1 points. So we're going through each 2D pixel coordinate of our features. And we're going to say that Z, which is our depth, we're going to take it right out of our depth 1 and index in, and we're going to say an integer version of round V, just in case that some of these have decimal places, which I think sometimes they do. So we want to make sure they're an integer data type, and then we're going to round the values to the nearest whole number using round here. And so we're rounding, converting to integers, and obviously because OpenCV thinks about pixels as UV coordinates, which is really X, Y, but whereas NumPy goes YX because it does rows then columns. So if you're thinking about an image as a NumPy array, then you have to switch where your indices are, as we've done here, where V is coming first because you have to go vertically and then horizontally in NumPy, but OpenCV always thinks in pixel coordinates, which are UV, which is X then Y. So I think, yeah. Okay, so essentially this is the pixel coordinate of the feature of interest. We're going to extract our pixel-wise depth information from our depth map that we generated using the stereo pair and get the depth information for the closest whole number pixel coordinate of the pixel coordinate of the feature that we're looking at right now. And then we're going to say if Z is greater than the max depth that we've set, which, as we know, means that it's a BS depth, that it's not a good estimate, we don't want to use it, then we're going to append the current index of the feature that we're talking about right now to delete for later, and then we're just going to say continue, which will come right back up to the top of the for loop again. So this is how we'll be filtering out features which have happened to be located in areas for which we don't have good depth estimates. Okay, and then so now it's time to reconstruct the 3D coordinate of this particular feature. So we know that this feature is in UV coordinates, which are pixel coordinates. So in order to get back into X and Y, what's the first thing we need to do to U and V to get back into X and Y? We need to subtract CX and CY from these values to move the origin back into the center. So we know that what we're going to be taking U minus CX, because as I laid out before, we added CX to move the origin this way. So now we're going to subtract CX to move the origin back into the center, and we're still in pixel units. So then we're going to divide by fx, which is the focal length in pixels of the camera, which is going to put us back into meters. And so that's what this will be, our new x value. So we Well, actually, no, I messed up. It's not in meters yet. It's actually unitless because we have pixels here. U is a pixel coordinate. We subtract cx in order to move the origin. Then we've divided by the focal length in pixels, which now gives us a unitless coordinate. And so we're going to multiply z into this because z is in meters. So altogether, x becomes in meters, which is what we want. And then so we're going to do the same thing to y. You multiply your depth back in, and we're going to say v minus cy divided by fy, which in this case fy and fx are the same, but no matter what camera you're using, this is the way you'd want to do it, because sometimes the pixels in the image sensor in a camera are not square, and if they're rectangular, fx and fy will be different. But in this case, I think they are the same. So either way, this is the way you want to do it. Right on. So I hope you see what's happening there. Is that we're the whole point of doing the stereo pair, the whole reason they put the stereo pair on the car is to get these depth estimates, because when a camera takes a picture of the 3D world, it creates a 2D image that doesn't have any depth information. And so knowing the depth is the only way that we're going to be able to figure out where we are in the 3D world. Otherwise, we don't have a scale that we're working with. And so, you know, more modern techniques involve using neural networks with monocular depth estimation, but stereo is still used widely, and it's effective without having to use neural networks. So this z value here is the whole point of a lot of what we've done here. And so because it expands things from that flat plane back out into the world wherever things are supposed to be. And so now we're looking at these visual features that we've detected in these images that we've matched using the descriptors that SIFT provides us by giving us histograms of gradient orientations for scale and rotation and variance. And we have now projected our x and y, and we had z. So now we have x, y, and z in meters. We have a 3D world that is constructed in the coordinate frame of this camera. So the camera where it is in the first frame that we're talking about here. So since we have now our x and y and z, we can go ahead and stack that onto our object points. So we'll say np.vstack, which is a vertical stack, and we'll take the old version of object points and then go ahead and stack on an array of x, y, and z. So that for every feature in its pixel coordinates, if we have a good depth estimation, meaning that the depth is not over 3,000, otherwise we'll skip it, then we come down here and we calculate our x and y values based off of our depth estimate, and then we append that 3D location in the world to our object points, which we will need to do what we're going to do. Okay. And so it's worth mentioning, and I'll just say this really quickly, is that technically you could have calculated x, y, and z by doing a np.linalg.invert_k, which is that intrinsic matrix, and then dotting that with z times a numpy array of u, v, and 1. So turning this into a homogeneous pixel coordinate into an array, multiplying the depth into that homogeneous pixel coordinate, and then taking the dot product with the inverse of k to go backwards from the projection from the 3D world into the image plane. Now you're reprojecting from the image plane back into the 3D world. So we could have said object points equals np.vstack of the previous object points and this, just like so. And because this XYZ array here is equivalent to taking this homogeneous pixel vector here and dotting it with the inverse of the K matrix. These will become the same thing. But like I said, having NumPy invert this K matrix is actually more computationally demanding than doing the algebra here by hand. So this is actually faster. And if you need proof of that, you should see the appendix in the notebook from the repository. As a matter of fact, I can just zip right down here. You can see Appendix A, where we show that the results are exactly the same between the two approaches, down to, you know, a million decimal places. But we can see that doing it with the np.linalg.invert k, it took 0.06 of a second, or rather 0.07 of a second, and doing it with the algebra, it took about half that. So worth keeping in mind as you move forward with doing this kind of thing. Okay, so we have a object point for that feature has been appended to the list. And remember, because this algorithm that we're about to use is essentially trying to figure out the pose of the camera in your second image with regards to the 3D locations of point with regard to some coordinate frame, but in this case we're choosing the coordinate frame of the camera's first position to relate all of these 3D points to, and then so the algorithm will return for us the pose of the camera in the second frame in relation to the coordinate frame of where it previously was. And so that will allow us to draw a trajectory out over time. So yeah, now that we have our object points figured out, we say image1 points equals np.delete. And we're going to take the old image1 points and delete the indices that we have been accumulating here for whatever features we had that happened to fall in places where we had a bogus depth estimate. And the reason to do it this way is because we want to keep our object points array in line with where the feature points are in these other arrays. And because we were counting I sequentially here without considering this I will correspond to all of the numeric indices of these arrays. So we can just use this compended list of indices to just go ahead and just snatch those bad ones right out. And we're doing that on dimension 0, which is the rows. So, and this is why. It's because what we're going to do here is, this is basically the workhorse of this entire operation that we've been working toward ever since the beginning of this video series, is that we're going to use what we've just calculated to use this cv2.SolvePnPRansac function. And this function will take in the 3D object points. Let me just keep this up so that we can sort of see what we're working with here. So the list of object points that we just created with our arithmetic and the image2 points, and remember, so these image2 points are still the 2D pixel locations of our features that we're tracking in the second image. And we didn't have to do anything to those because this algorithm expects the features in the second image to be in 2D pixel coordinates. So we don't have to worry about reprojecting those into 3D space. This is how it works. And this is why we took this step to use np.delete to take the bad features out and just like remove them straight out of the list, which collapses it down to being a array that matches perfectly with this array that we've accumulated here of our good 3D points. And so now object points and image2 points, they line up after we've run this np.delete and take out these indices. Now this and this array match up row for row of our features that we're still tracking and not the ones that we're ignoring. And we also have to pass in the camera matrix here. And then disk coefficients is distortion coefficients, which you might have if you had calibrated your camera using chessboard images. And in this case, we're not going to because I believe that the KITTI dataset is already calibrated. So, and they don't provide any of the chessboard pictures. And then none for, for disk coefficients, because this isn't an optional parameter here for whatever reason. So we're not going to use any, so we say none. And so, that's it. This is like all the work that we've done so far has basically been to get to this point, to have 3D object points in the 3D world that we can then solve for the correct rotation. Well, in this case, it's going to give us a rotation vector of, I think it's in axis angle form. And so we're going to have to turn that into a rotation matrix. And the translation vector that will explain where these points are found on the 2D image plane in the second image. And now the way SolvePnPRansac works is that it's a perspective endpoint algorithm, which basically it takes the minimum number of points that it needs to solve for the transformation, which explains where these features are found in the second image. And then it takes that solution that it comes up with and it checks to see how many of your features agree, which means they fall within an error margin from where its reprojection of those points are according to its solution. And if the number of inliers, meaning the number of points which agree with its solution, is not above this, if we pull this doc string back up, this, you can set this by hand, is I think inliers is the one. I just had actually I have it pulled up over here. Inliers is, no. Okay, I think that it's the reprojection error. So this is going to be the minimum number of inliers. So it's a little confusing because this guy over here said min inliers count, which I don't see. So he's got that wrong. Must be an old version. Yeah, so inlier threshold value used by maximum distance. We'll just kind of, you can look further into this on your own. The fact is, it's doing most of this under the hood, which is fantastic, which means we don't have to do it by hand. But essentially, it picks, I'll run through what I said again real quick because I kind of interrupted myself. It picks the minimum number of points it needs to solve for the transformation, which explains where those points are now found in the second image. Then it uses the solution it comes up with to check all of your matches, and then it figures out how many of them agree within a certain error threshold with the solution that it came up with. And if the number of agreeing samples, or rather agreed points from your features is above a certain threshold, then it decides that that solution was a pretty good one. And then it takes all of the inliers that agreed together and then makes a new solution that uses all of those inliers. And what this is so that's what RANSAC stands for, is random sample consensus. So it takes a random sample, comes up with a solution, tests that solution against the whole batch, and figures out how well it explains the batch based on how many inliers that solution produces. And if the number of inliers that solution produces is above its threshold, then it says, okay, we'll take all of those inliers because those are all, agree with one another, and then we'll solve to figure out a solution for all of these inliers. And in doing so, it effectively figures out which points are outliers, meaning which ones have been sort of erroneously matched, which is it's super effective at weeding out the feature matches that we have that aren't actually any good, because it figures out which of these feature matches agree with each other when you move the camera a certain way, and then any of these outliers that don't get along with that, it assumes there must be some problem there, we'll just ignore them. And this is a very effective way of handling outliers. And so that's the whole point of RANSAC. And as a matter of fact, RANSAC is used a lot in multiple applications in computer photogrammetric computer vision. So, and here it is doing its job very well. So yeah. And so, as I said before, the RVEC that this returns is not a rotation matrix the way that we want it to be. We want a 3x3 rotation matrix because we want to build our, let me grab this and zoom to the top here. We want RT, we want our transformation matrix, and R is in this is a 3x3 rotation matrix. So we don't want an R vector, we want an R mat. And so we need to turn our R vector into an R mat, and luckily CV2 has just the function to do that. So we'll say R mat equals cv2.rodriguez RVEC, and then we want the first item that returns. And so just we'll pull up a doc string hopefully here, and it's the Rodriguez formula to does exactly this. I don't know why I used a Q there. Yeah, so converts a rotation matrix to a rotation vector, or vice versa. So exactly what we want. And so it automatically determines whether you've passed a vector or a matrix. And then of the things that it returns, which these doc strings are a bit of a mess with OpenCV and Python, but take my word for it. We want the first item that it returns, which will be the 3x3 rotation matrix, which we're looking for. And so there we have it. We now have a rotation matrix and a translation vector, which best explains the movement of the camera between the first frame that we look at and the second frame that we look at, using the features that we detected using SIFT and described using SIFT, matched using the distance between those descriptor vectors from the SIFT process. And then now we have solved for the best explanation of rotation and translation of the camera, which explains the movement of those features between one image and another. And we've done so in a metric way, so in using our Z, which is our depth that we calculated from our stereo pair. And so the output of this function will say return rmat tvec and image 1 points and image 2 points, just in case we need them for any reason. But really, this is what we wanted: rmat and tvec. This is everything. This is what we've been working so hard on. And so let me see how long this video has been. Looks like we're at 44 minutes. So the next step is going to be pretty lengthy, probably, I don't know if it will or not. Let's break this apart so it's a little more digestible and really let this set in what we've done here, because essentially all we have to do from here is iterate this for every single frame in the sequence of images that we have in this data set, or rather the sequence from this data set. And so we're going to use this function that we've just now made to iterate, use this function once per frame, and then add all of these little changes in camera pose together to recreate the trajectory of the camera over time using what we've done here. And so we can test our function real quick just to make sure there's no errors. So let's say estimate motion. So we're going to need our camera intrinsic matrix. So our handler has a PO matrix. And as we covered in the first video, if we say cv2.decompose projection matrix, which is what that is, it will produce for us a few different things. But the first thing it produces is K, which is what we need, which is the intrinsic matrix. And the second one is the rotation matrix, translation vector, and then I think 4 more things that we're not going to really talk about that are returned from this function. And so now if we look at K, this is an intrinsic matrix. And like, to see for sure, these are the focal length in pixels, X and Y, and they are the same as I mentioned. This is the center of the image in X, center of the image in Y. And this is what we use to do our arithmetic up here, which we're about to pass into the function. So we need our list of matches, and we made some matches earlier. I'm going to rerun because obviously we don't want to use orb. So I'm going to rerun this cell where we did it with SIFT, and I used a distance ratio filter of 0.3, which is pretty stern, but it gives us really good matches. And so now matches is our list of matches that we want. So we'll pass that in to the function, matches. Then we need our key points from the first image and our key points from the second image. Sorry, where are we? Okay, yeah. So we want key points 1, key points 2, K, depth, and our max depth, which is already set for us. So as we can see, I called them key point 0 and key point 1 here. And so we'll just pass those right in. Key point 0, key points 1, and then we should have a depth around here somewhere. Let's go up. It's probably just called depth, so we want to make sure. Yeah, here it is, depth. Pass depth. And then we don't need to set max depth because we already decided on a value. And so this is going to return rmat tvec image 1 points, image 2 points equals this. And then we can take a quick look at our rotation matrix. And then translation vector. All right, let's just take a look. Oops, depth 1. Why would it say that? Because, oh, K has to be in here. Okay. So we have a rotation matrix and a translation vector, which are in the shape that we would expect. Let's go ahead and round these just for the sake of ocular pleasure. Okay, yeah. So here we have a rotation matrix and a translation vector. So let's just take a look at what these two look like if we horizontally stack them into a transformation matrix. And I'll just call it that. Why not? And we'll say np.hstack, and we'll say rmat and tvec. Now let's look at transformation. Oops. Dot round 4. See what it looks like. Okay, so this is a 3x4 transformation matrix, which is the shape that we would be expecting, because that's the way that the dataset tracks the pose of our camera. So let's see how this compares to the first pose given by the ground truth, which we have conveniently attached to our handler as GT, and we'll take not the first entry, we need the second entry because that's what we just solved for, and round that to 4 and use the print statement so it looks a little cleaner. Okay, so we can see that these aren't the same, and the reason is because the ground truth is being tracked in the first position of the camera's coordinate frame, and then the second ground truth will be the origin of the camera, where that is in relation to the first coordinate frame. And what we have solved for is actually where the coordinate, the origin of the camera in its first position is in the new camera's coordinate frame. So actually we've solved this backwards, but we can easily reverse this. And this is all about what we're going to do in the next video. So I'm going to leave it at this, but check this out. So we can actually invert a transformation matrix to go in the other direction. And we can do that by making it into a homogeneous transformation matrix. And we can do that by, so we'll call it HomogTransMat equals, and I'm going to start with an identity matrix, which is 4x4, because remember, we can only invert a square matrix. And so this is why we're doing this. It's just homogeneous things that it's just like cheating. It's awesome. And so we'll make a 4 identity matrix, and we can see what that looks like real quick, which is just, you know, 4x4 array with ones down this way. And what we'll do is we'll say HomTransMat, and we'll say the first 3 rows and first 3 columns are equal to our RMAT that we got before. And then we'll say HomTransMat, the last column, or rather first 3 rows, last column will be equal to the tvec. And then let's see what that looks like. Oops, what happened? Might have to reshape. Make it more one. What shape is tvec? Okay, it should be, that should be good. I don't know why it's giving me trouble. Let's just consider this. What's going on here? We can figure this out. No big deal. Let me just try a .t here. Okay, well that worked. Okay, so this looks like what we had before when we did the horizontal stack. So this is our 3x4 transformation matrix, which is really what we're after. But like I said, we're taking that and making it into a homogeneous transformation matrix by adding this row on the bottom here of zeros and then a 1 at the end, which I, you know, abused the identity matrix, and basically we just replaced these 3, or this 3x3 portion here with the RMAT, and I replaced this these three numbers with the t back. And so that gave us this. So what happens if we take np.linalg.invert hom transformation matrix? What does that look like? And round it to 4 here. Okay, so still doesn't look like what I'm expecting it to. I'm probably indexing the thing wrong. Because, let me see, handler.groundTruth0.round to 4 places is, yeah, it's just a bunch of zeros and ones because the camera hasn't moved yet, so I think, yeah, it's just throwing me off because of this scientific notation that it's using here. It's not using it here. So, and it's also possible that we're just not getting like that close, but it doesn't seem like it should be that far off. Kind of opened up a can of worms on this one. I don't want to leave off on a bad note here. It's kind of messed up what I was doing. So just bear with me for 1 second here because I got to figure out what I've done wrong. Okay. Oh, you know what it is? I think that I have to dot this with the original. So we can see here that handler, the first ground truth is just like an identity matrix, rotation matrix with this 0 transformation matrix here. So I'm going to turn that into a homogeneous start by saying np.i 4 like we did before, and then hom start, and I want to say the first 3 rows, all of the columns equals handler.groundTruth0, and then we're going to say first, or rather second pose, let's call it second pose equals hom start dot with this np.linalg of the what we came up with earlier. And then let's take a look at second pose now, round to 4 places. That's exactly the same. Yeah, it may just be that what we're dealing with here is that the error on the first frame is pretty bad, and that's why they don't look exactly the same. You know, it does seem strange to me that it's that far off, but oh, okay. Yeah, I see what it is now. So I'm using the generators here, where image +1, second image left. Yeah. Okay. No, that shouldn't be it then. I don't know, man. I can't believe I was so ready to finish this video, and then I worked myself into a corner here. So yeah, I don't really. I think that the issue is really just that there's error between our estimate and in the first position. Because I mean, we can see here if we go over to what ends up happening, you know, we can see that error starts accumulating, you know, pretty quick in our estimates here, but not that fast. I mean, it doesn't seem like it should be off by that much. I've made some kind of error here, and I'm just kind of like flailing trying to figure it out because you know this is the ground truth of what it should look like. I inverted it, and you know the that's just fine and whatever. So it's just a little off. That's all it is. It's just that, you know, this process that we're doing here is not perfect. So let me just run these cells again, see if it cleans up any. And really, I think that what we're looking at here is just that the difference between the two is just the error inherent in this process. I didn't really prepare this comparison, obviously, or else I would have had something a little better looking. But yeah, so we have image left is the first image left, first image right. We didn't even need that. Image plus one is the second image left. We're extracting the features from image left and image plus one, matching the features with the descriptors. And then we're filtering the matches distance, timing it, so it should be pretty cut and dry there. We have estimate motion, KP1 and KP2, K depth, max depth, and yeah, this is what happens when you're freestyling. So zeros. This should all be right. Anyways, maybe I'll just figure this out before the next video. I mean, everything we've done here is right. I think that really I was just expecting probably the error, like the ground truth to look more like what we came up with. But if we look here, it's the -2. So yeah, I mean, we're off by, you know, fractions of a meter or whatever, but we can see that, you know, to some extent, these are not that different. So let me suppress np.print options, and we'll say suppress. I thought it was suppress. Print options, suppress. Yeah, suppress equals true, and for some reason it didn't autocomplete, but whatever. Suppress equals true. And it's not listening. That's supposed to suppress the scientific notation. Whatever, man. Killing me, man. Killing me. All right, so we'll just look at this again. Let's, you know, we've got -1.2 to e to the -3 over here. We can see that we have 2 to the e to the -3 over here. If we, you know, look at 1, 2, 3, and here we have -2.1 e to the -3. So instead of 2.1, we have 3.3. The 1, 1, and 1 going down this way is pretty close to the ground truth here. So, I mean, we're actually not that far off. I guess maybe a minute ago I was expecting this to look just a little neater, but you know, we're doing visual odometry here. It's going to have errors, and ultimately it's going to be pretty close. So what's happened is that we just have some error between the first and second frame, and but it's not that far off. For instance, yeah, see, I mean, it's like, 0.85, we got 0.66, and we're talking about meters. So, what is 0.858 minus 0.667 meters is, okay, and then we'll multiply the result of that by how many feet are in a meter, which is 3.28. Oops, I'll do this. Yeah, so we're off by like a half a foot in our first frame. So, granted, there could be some error here that I'm missing, but like I don't want to I feel like I've already spent 10 minutes just like kind of looking like an idiot here. Take my word for it that this is going to work out fine. It's just that you're doing visual odometry with depth estimations from stereo, and you're using feature matches. This is not necessarily, I mean, like I showed you, this is the result. So we're not going to get perfect results here. There will be accumulated error. The pose and our estimates will be off, but we're laying out the fundamentals of how this thing works, right? So we can't expect perfect results. So I'm going to end the video there. In the next video, we're going to get into how to do this iteratively and how to reconstruct the trajectory of the camera through time by doing this on every frame, and then combining all of the trajectory estimates into a single trajectory that are all in the single coordinate frame of the camera's first position. So I hope you enjoyed this video, and watching me do all this. So I'll see you in the next video, and we'll put a bow on this thing. So see you next time.